Hello, and welcome to TI's Low EMI training series. I'm Sam Jaffe, and in this short video, we'll be discussing how you can reduce your EMI filter size and cost with our feature called AEF, Active EMI Filter. First, let's talk about EMI filters, what they are, and why we need them. And for this video, we will focus on low frequency EMI, which will be conducted differential mode EMI below about 30 MHz. A buck regulator is a switching regulator which generates noise at the switching frequency, generally hundreds of kilohertz up to a couple megahertz, and generates noise at that frequency's harmonics. For a general case, the inductor current, shown in light blue, is a triangle wave. The rising slope is supplied from the input current In dark blue. This current ripple on the input causes a voltage ripple on Vin. This ripple can make its way back to the supply, in this case a battery, which can interfere with other circuitry powered by this supply. So we'd like to reduce this ripple to avoid interfering with other systems. We can do this by adding capacitance on the input, like Cin. To further filter the ripple, we can place an inductor in series with the supply and add more capacitance. This is called a passive EMI filter. The resistor is there to dampen any resonance with the capacitors and the inductor, but this can come from the ESR of a bulk capacitor or other combinations of capacitors and resistors. This is the typical approach for most automotive and industrial systems which need to meet certain EMI specifications. The good news is that if the EMI test fails, you can just add more inductance or more capacitance to further reduce the EMI, which will resolve the issue. The problem, however, is the cost. More inductance and capacitance is expensive, both in price and in board area. To address this, you can switch at a higher switching frequency, but then the high frequency EMI will be more of a concern. Or you can find a device with spread spectrum, which will reduce the fundamental by a few dB microvolts, but that might not be enough attenuation for your desired solution. Another approach is to use a two-phase device, or two devices 180 degrees out of phase, called interleaving, which greatly reduces this ripple, but that can add even more cost. So what else can we do? We can use a new feature from TI called Active EMI Filter, or AEF, which can provide significant benefit in low frequency EMI performance and can enable a significant reduction in filter size and cost. It works by sensing the supply voltage ripple and injecting a signal proportional to the inverse of the ripple to cancel it out. If Vin EMI ripples up, AEF sinks current to bring it back down. If Vin EMI ripples down, AEF sources current to bring it back up. It's essentially resisting changes in voltage, which is exactly what a capacitor does, but AEF has the ability to sink and source current at the scale of a very large capacitance while being constructed from small, inexpensive circuitry. And here's what AEF looks like in a real schematic. We see that the buck regulator has a sense pin and an inject pin for sensing Vin EMI and injecting current to cancel the ripple. The compensation network, circled in red, ensures the filter remains stable, targets the desired frequencies, and injects the optimal amount of current. All of these components can be a small 0603 package or smaller, which keeps the size and cost to a minimum. Now, let's check out what kind of results we can get with AEF. How much can we improve our EMI result, and how much can we reduce our filter size? Here, we can see test board results for low-frequency conducted EMI to CISPR 25 Class 5 standards. Both tests are taken on the same board with the same small passive EMI filter, but the plot on the left has AEF disabled, and the plot on the right has AEF enabled. We can see the fundamental frequency of 2 MHz is attenuated by 17 to 18 dB microvolts, and the second harmonic is attenuated by about 10 dB microvolts. We can also see the low frequency noise below the fundamental is greatly reduced as well. To get this kind of subharmonic attenuation, we would need a lot of inductance and capacitance on the input filter. The active EMI filter, on the other hand, is easily able to achieve this performance. The benefit is even more pronounced at lower switching frequencies. Here's a side-by-side comparison of two filters for a board switching at 400 kHz. The passive-only filter EMI emissions are about 20 dB microvolts worse at the fundamental frequency compared to the reduced filter with AEF. The board images on the left show the passive-only filter, and the board images on the right show the size-reduced passive filter with AEF. The reduced inductance for the AEF filter allows for an inductor with a smaller footprint and reduced height compared to the passive-only filter inductor. Additionally, the combined area of the 0402 and 0603 passives from the AEF compensation network are also smaller than the 0805 and 1210 capacitors required on the passive-only filter. And that's not to mention the cost savings. Cost is reduced considerably by the size reduction of the inductor and the ability to replace the input capacitors with less expensive passives. Also consider, not only do the passive-only filter capacitors need to be rated for a particular capacitance, they must also be rated for the maximum input voltage or greater, while most of the AEF passives require much lower voltage ratings, which further reduces the cost of the total AEF filter. The overall solution area reduction is 50% and the volume reduction is 66%, on top of that 20 dB microvolt improvement at the fundamental frequency. And here's one more example comparing AEF to passive only. On the left, we have the LM25149 evaluation board. This is the top view and the filters on the back. On the right, we have the older generation LM5141 evaluation board with a passive only filter. Both achieve similar low frequency EMI performance. Again, we see that the total AEF filter size, even including the AEF compensation network, is significantly smaller and less expensive than what we'd see on a passive-only filter with comparable performance. As you can see from these results, AEF has the capability to significantly reduce your low-frequency EMI emissions and can cut your EMI filter size and cost into a fraction of what it was before. Next time you upsize an input EMI filter to meet low-frequency emissions, or if you're thinking of starting a design and would love to pick out a less expensive filter, remember our active EMI filter feature and consider designing with a device which is actively helping you reduce your solution size, cost, and EMI emissions. That concludes our video on active EMI filter. Be sure to check out our other videos in our EMI series to become an expert in power design with EMI in mind. Thanks for watching.